Sure. Thank you for the introduction. I'll just dive deep into explaining about the topic today. Let me just share. I hope my screen's visible.
Yes, ma'am, it is.
Yeah, it's okay. Before diving deep into understanding each topic at once, I'll just give a brief of the discussion that we'll be having today. We'll be knowing a bit about what is multi-class classification, where in real life we can actually use this algorithm, how to perform multi-class classification, what are different techniques that are in broad terms used, how do we evaluate problems like multi-class classification, differentiating them with respect to binary classification, which we have been knowing about for a very long time. And one of the major problems with multi-class classification involving imbalanced data sets and how do we deal with them. Moving on from multi-class to multi-label classification, we'll find out the difference between these two algorithms and again diving deep into their application techniques and evaluation techniques. Once we know a little bit of theory in depth about what these algorithms are, how do these algorithms work, we'll dive deep into the hands-on notebook sessions where we'll be taking up few data sets and then evaluating and running different algorithms on top of this. So I hope this content is clear and then we can go deeper into that. Starting with multi-class classification problem. So as we all know that binary classification is a form of supervised machine learning where we are asked to predict between two classes, like for example, identifying whether a sentiment is positive or negative, or identifying whether a picture is of a cat or a dog, When we tend to increase this problem subset to include more than two classes, this tends to become a multi-class classification problem. The algorithm where we try to predict more than two classes, where multiple classes are supposed to be predicted, and for one single output, there can only be one class that can be predicted out of it. Some real life applications for this multi-class classification involve image classification, like for example, predicting whether a certain image belongs to which animal or whether a certain image is belonging to which number. The famous MNIST dataset that we have belongs to 0 to 9 numbers, and then we predict whether an image belongs to a certain number. The optical character recognition, sentiment prediction, binary classification problem would involve predicting whether a particular text or a particular review is of the sentiment positive or negative. If we actually want to go deeper into sentiment analysis, identifying whether the sentiment involves a happy, sad, depressed, angry, or multiple other emotions, we tend to move towards a multi-class classification label. Medical severity diagnosis, identifying whether a disease belongs to a low, mid, or a high severity based on the parameters captured. A product category classification, like for example, identifying whether a book belongs to a fiction or a non-fiction or some other science or some other academic genre. Text intent classification, identifying the intent out of a text. We can have multiple intents on like how chatbots work. They identify multiple intents and then we deep dive into this and identify the intent out of the text. Considering all of these applications where multi-class classifiers work, how do we actually do multi-class classification in the real world? So there are some inherent multi-class classifiers, like for example, KNNs, random forest classifiers, XGBoost, naive-Bayes. These classifiers have been used for supervised learning problems, and they are also, along with binary classification, they also give a scope of identifying multiple classes out of these. All of these provide the chance for inputting in multiple labels and generating out the data. Now, when the data starts to become huge with, let's say, multiple classes coming in, like for example, rather than having just 3 or 4 classes to predict, we are given with a data set which involves predicting from hundreds of classes. We tend to move towards an ensemble of binary classifiers rather than just using a single classifier, like for example, a KNN, K nearest neighbor classifier, or a random forest classifier. We tend to move towards considering multiple binary classifiers. There are multiple ensemble of binary classifier techniques available, like for example, one versus rest classifiers, which involves few XGBoost classifiers or SVM classifiers. Now, how do these one versus rest techniques work? So the inherent concept that is applied is that we want to train multiple binary classifiers for each of these classes. And once each of these binary classifiers are captured, we tend to figure out the maximum prediction that can be identified. So for example, in this particular image, we are given with 3 classes that we have to identify. A very easy way to identify these 3 classes is to pass it on to, let's say, a random forest classifier and identify the output and get a final label out of it, whether it belongs to class 1, class 2, or class 3. If we are given with a few more classes and we want to use a one versus rest technique, how do we move on to this is we train 3 different binary classifiers. The goal of each classifier is to predict whether this particular class, let's say classifier 1 goals is to predict whether class 1 is present in the data. Classifier 2 is to predict whether class 2 is present in the data. So if it's present, it outputs a label 1. If it's not, it outputs a label of 0. Classifier 3, the goal of classifier 3 is to identify whether this particular class 3 is available in the data. So once we have all these 3 classifiers, as you all might know that in case of binary classification, we are given with a probability metric, which on applying a certain threshold, we then divide whether it's a 1 or a 0 label. Let's say we get a probability label of 0.9, 0.8, and 0.7 for each of these binary labels. Now, we actually identify based on the maximum probability identified out of each of these binary labels, we figure out that this particular data point belongs to class 1, considering this has the maximum probability. So this has also been explained by using these 4 classes here, where we have 4 different, captures here. And once we train these different binary classifiers and once we get all these probability numbers, we tend to figure out what is the final outcome for each of these data points. Yeah. Other than using one versus rest classifiers, which are mostly used in logistic regression kind of numbers, including multiple binary classifiers, there's also one more technique that we can use is one versus one classifier. Let's say the goal of one versus rest classifier involves training 4 to 5 multiple different classifiers. But in case of data sets where there's an imbalance, for example, we have a data set where one certain class has a lot of data, let's say hundreds of data, but another class is present in minority and has only tens or 20 or numbers of data. Now, in such cases where there's data set tends to be in the form of imbalanced data set, it is generally advised to go for a one versus one classifier. Now, one versus rest classifier would figure out the number of binary classifiers based on the number of classes. So for example, if our goal is to predict whether a certain image or a certain text belongs to which of these 4 classes, we'll have 4 different binary classifiers. But in cases where data is imbalanced and we are trying to move forward to one versus one classifier, we will have the number of binary classification models according to this formula, which involves n into n minus 1 by 2. Here, n refers to the number of total classes. So for example, if you look at this image for a 4-class binary classifier model, where we have to identify whether this particular belongs to an apple, a pear, orange, or a banana, we'll have 6 binary classification models with pair of 2 different fruits. Now, out of all these 6 different classification models, we'll have multiple probabilities output, and then we calculate the maximum probability given for each of these class, and then figure out which class is supposed to be outcome from that particular input data. So each binary classification model will predict one class label, and then we vote it out. Let's say we have these 6 binary classification models, and 4 of them actually predict that it is an apple. So based on the majority voting, the image or whatever label is identified as an apple. Okay. Now, after looking at the techniques, different one versus rest, one versus one, And then also inherent classification techniques that we have looked at, which are generally used for multi-class classification problems. Now comes the problem of evaluation. How do we evaluate multi-class classification labels? So one of the major challenges that come up is imbalanced data sets. Now with balanced data sets, a very simple metric to evaluate is accuracy, that is identifying how much is correctly predicted, true positive plus true negatives out of the entire corpus. But accuracy will not be considered as the best metric when it comes to imbalanced datasets, because it might happen that one class which is in majority will be predicted very often correctly, and the class which is in minority might have incorrect outcomes. Now, if we are combining true positives plus true negatives, what will happen is we'll still get a higher accuracy number of, let's say, 0.97 plus or 0.96, but we won't be doing good on the minority class. So a better way of evaluating such numbers is to capture a precision, recall, F1, and AUC values. Now, as we know that precision tends to figure out the true positives by true positive plus false positive, and recall tends to figure out true positives by true positive plus false negatives. So when we tend to go for imbalanced datasets, for each of these class, we'll be able to identify the precision recall numbers, and we will be also able to capture whether a precision is high or a recall is high, and then how we are going to make changes in order to accommodate for the minority class. So on the right hand side, we have a confusion matrix for people who are not so much aware about what a confusion matrix is. Once we have all the predictions, we design this confusion matrix to capture all of the matrix that are available on the left side. So I'll just give a brief of how this can be done. Let's say you have a particular data set which is actually giving you this kind of confusion matrix. So what it means is that you have a data set with a cat, fish, and hen that is supposed to be predicted. On the true side, we have 4 samples for cat, 6 samples for fish, and 3 samples for hen, right? Now, once we generate this confusion matrix, we identify how much of each of these class goes into another class. So for each of this cell, for example, this cell would mean that a label which was actually labeled as class, a cat, is identified as a cat. So 4 out of the total is actually labeled as cat, is actually predicted as cat. 6 out of the total, which is predicted as cat, it was actually labeled. Okay, so let me go one by one. So out of the true labeled cat labels, which is 4 plus 1 plus 1, 4 got correctly labeled, 1 was incorrectly labeled as fish, and 1 was incorrectly labeled as hen. Now out of this 6 plus 2, which was actually labeled as fish, 6 got incorrectly labeled as cat, 2 got correctly labeled as fish, and 2 got incorrectly labeled as hen. Similarly, out of this 3 plus 6, which was actually labeled as hen, 3 got incorrectly labeled as cat, 0 got incorrectly labeled as fish, and 6 got correctly labeled as hen. So once we identify these, it becomes very clear for us to actually capture the precision, recall, and F1 value for each of these class separately. Okay. We got to know about, for imbalanced data sets, how we can convert different evaluation metrics. There's this library called imlearn, which has multiple techniques that are available in the form where we can actually modify our data set, convert it into a balanced data set. And once a data set is balanced, we can run multiple algorithms. So one definite way is to select a different evaluation metric. Let's say if our data is still imbalanced, such as an F1 score over an accuracy number. But in order to make our data more balanced, few techniques that we can use are random undersampling the majority class. Let's say we have one particular data class which has 1,000 data points, another data class has 100, and another data class is 20. Now we want to undersample the majority class in order to make it more comparable to other 2 classes. Or we want to oversample the minority class. We want to convert the 20 data points in order to increase it up to 100 or increase it up to even more in order to make sure that all of these classes are properly balanced. So oversampling can involve either random oversampling, which would mean that we just keep on duplicating those data points up till we reach the number that we want, or a smooth technique. Smooth technique involves synthetic minority oversampling, which not just does the duplication, but generates new data points by altering certain things in the feature vector. So it's not just exact duplicate of the data, which can lead to overfitting on that particular data, but rather generating newer data out of the existing data point. We can also use atomic links, which is for the undersampling. What atomic links does it identifies the pairs out of majority and minority class, which are very close to each other, and then removes the majority class pairs, the numbers from the majority class, in order to make sure that the numbers which are present on the borderline are removed. We can also do a cost sensitive training. That is, we can penalize the algorithms to increase the cost of classification. So while we have our loss function, we can do a weighted loss function for each of the classes. We can identify more weights to the minority class and then do the training in order to ensure that, we get better results for the minority class. So this was all about multi-class classification. We got to know more detail about, how multi-class classification works, how we can evaluate them, what are the nuances that are handled with multi-class classification. Now we can switch on to multi-label classification. So multi-label classification are kind of classification techniques where we can identify multiple outputs from the label, but these multiple outputs are not very mutually exclusive. So one data point can have multiple labels out of it. So if you look at this image, a binary classifier will have two classes, out of which one will be correct. A multi-class classifier will have, say, L classes, out of which one will be correct. But a multi-label classifier will have, say, L classes, and out of which multiple classes can be correct. So one data point can be marked onto 2 classes, 3 classes, 4 classes, or many more classes. So multi-label problems, multiple classes are identified. For example, a book can belong to fiction or a non-fiction genre, but it cannot be both at the same time. But a certain book can belong to a romance, mystery, thriller, or drama, these kind of multiple genres at the same time. So when we want to identify romance, mystery, thriller, drama, and some other genres from one certain data point, we tend to move towards a multi-label classifier. So multi-label class. So for example, in this image, as you can see, we have action, adventure, and fantasy. These labels are allotted to this Doctor Strange movie, which means that there can be multiple labels that are assigned to this particular movie. Now this PG-13, if you can see over here, this is the kind of tag that's assigned to that particular movie. There can only be a one tag that can be given for a particular movie. So this will be identified through a multi-class classifier, while these labels like action, adventure, and fantasy can be identified by a multi-label classifier. I hope this clarifies the difference between a multi-class and a multi-label classifier. So what happens in case of a multi-class classifier, let's say we are using artificial neural networks, and then we have a softmax layer at the end, which identifies out of, let's say, 4 classes, it identifies the probability vector and then gives out the maximum number. But here, what we do is, instead of having one softmax, we have multiple sigmoid activations for each of these nodes. So each of these nodes are then identified in the form of using a cross entropy loss function. Each of these nodes can give out one certain output label. So let me explain this once. Okay. Let's say this is an artificial neural network, right? Now, if you want to go and do a multi-class classifier, so this is a 3 output label. So a multi-class classifier will give you, let's say, 0.9 or 0.8. Okay, one second. Let me use a text to explain this better. So 0.9, not 0.8, sorry, 0.9, 0.05, and then 0.05. If it's a multi-class classifier, we will be getting an output like this, which will inherently sum up to 1, because we know that the output of a softmax sums up to 1. So out of these 3 classes, we can then identify that this particular input belongs to Y1, that is the first layer here. But if it's a multi-label classifier, what happens is, for each of these nodes, so for example, for this particular node over here, we will be having a binary classification value. So for Y1, we will be applying a sigmoid over here, and we will be giving out a certain probability number. Then for this particular node, we'll again apply a sigmoid and we will be giving out a certain probability number. Then again, for this particular class, we'll be again applying a binary sigmoid over here and we'll be giving out a probability number. Now, this might not have, they do not need to sum up to 1, but the probabilities, we can have multiple probability numbers there. And then for each of these, we can then identify which of the, belongs to 1. So this particular output can have an output like 1 and 0. And based on the probabilities generated, we can label them as, so let's say we keep a threshold of 0.5. Then if we get a number as 0.9, and then for this we get, let's say 0.2, and for 0 we get 0.1, right? Now these need not sum up to 1, but if we get certain probability numbers like this, and then if we do a thresholding at 0.5, our actual output score could come out as 1, 0, and 0, right? And then once we get these probability numbers, so this can become the Y pred then over there. So once we get these numbers, what we can do is, this is our Y actual output. Then we do a back propagation. We do a binary cross entropy for each of these and then do back propagation, keep on generating the gradients. So I think this clarifies the difference over how in a different way multi-label classification happens while as compared to a multi-class classifier. Okay. Going back to our actual PPT. Yeah. Okay. Now, few applications of multi-label classification. So multi-label classification problems are have inherently come into picture because of major text categorization topics. So categorizing a certain document into multiple topics, say whether that document can have multiple tags associated with it. Let's say it's a scientific journal, which also talks about COVID, or which also talks about machine learning, which also talks about some other detail. So it can have multiple tags associated to it, and these tags are then identified via multi-label classifier. Identifying multiple objects out of an image. So object detection kind of techniques where, in a certain image, you can have trees, you can have a sun, you can have a mountain, you can have a river. So you can identify you can have a ball place. So you can identify each of these objects out of an image. Classification of genes. Audio categorization, like for example, you have an audio, you want to tag it to multiple tags, like that particular audio is a relaxing, calm, happy mood kind of audio. So it can actually be assigned those different tags all together at once. How do we actually do a multi-label classification? So multi-label classification problems are there are basically 3 methods to solve it. One is a problem transformation. So this problem transformation can further be divided into, say, binary relevance, classifier chains, and label parset. I'll dive deep into each of these techniques. Adapted algorithms. Adapted algorithms actually mean that there are certain, so these supervised algorithms like KNNs, they have been adapted to perform multi-label classification inherently. So we can use scikit-learn, so scikit multi-learn library basically in order to perform a multi-label classification using a multi-MLKNN algorithm. Ensemble approaches, there are different ensemble approaches which can be used in order to perform multi-label classification. So let me explain deeply what each of these binary relevance, classifier chains, and label parset mean. I'll be using a blog to explain this. Let me just open this to become more clear. So binary relevance is a very simplest technique, right? So what it does is each of these label is considered as a separate single class classification problem. So let's say you have these 4 labels, right? And you have these data points which belong to, let's say X1 is a data point which belongs to Y2 and Y3. Now X2 is a data point which belongs to just Y1. Let's say you have multiple data points like these. And then what we do is this problem is broken into 4 different single class classification problems. So now you have to figure out that which out of all these data points, how many data points belong to Y1. Then you figure out how many of these data points belong to Y2, how many belong to Y3, and how many belong to Y4. And then once you get these numbers, you sum these outputs basically in the form of a vector. And then you can identify that, let's say X1 also belongs to Y2 and Y3, and it is also predicted in the same format. So you get the output as 0, 1, 1, 0. The multi-learn library will provide the implementation. They've also provided a certain implementation using the Scikit multi-learn library, where you can use a binary relevance in the form of a Gaussian naive-based classifier and then fit on top of it. So I hope the idea is clear. The basic idea is to get the how many number of labels we want to predict. So let's say there are 4 classes, then we'll have 4 different single class classifiers. We'll predict for each of these, and then we'll get the final vector output. Now, another metric that we want to go for is a classifier chains. What happens with these is we separately identify for each of these classes, right? We do it separately for class 1, separately for class 2, separately for class 3, and separately for class 4. But this will not involve the correlation that's present in between the classes. So for example, if an object detection in an object detection kind of an image, if there's a boy standing holding the hands of someone else, then those holding hands kind of show a correlation that because of this boy standing, the other object can be identified. In order to capture this correlation, we use a classifier chain technique. So rather than doing separately on 4 classes, our problem is transformed as such that once we generate it for Y1 based on these data points, now this X plus Y1 becomes our new data point, new feature vector, which can be used for Y2 prediction. Once we do it for Y2, X, Y1, and Y2 becomes a newer data point, which becomes here for Y3 prediction. So rather than using 4 separate classifiers in parallel, here we do 4 separate classifiers in a chained manner, that is one on top of the other. And when the other one comes, we use the older one as one of the feature vectors. So this can actually capture the correlation that's present in between these different classes. The third one is label power set. So label power set is nothing, but we just convert this problem into a multi-class problem. So we have one multi-class classifier, which can identify whether one data point belongs to which particular out of these classes. And then we have multiple such classifiers. So let's say we want to identify a unique label combination in the training data. So we have this particular data point, right? X1, X2, X3, X4, X5, X6. Now we find that X1 and X4 will have the same labels, right? Y2 and Y3. X3 and X6 will have the same set of labels. So what label power set will do is it will convert. So Y2, Y3 will become one such label. So Y2, 1 and Y3, 1 becomes one label. Similarly, let's say Y2, 1 becomes one such label. So based on our data, we first generate how many labels are there. So okay, so 0, 1, 1, 0 is considered as 1. So this particular combination is one such label. 1, 0, 0, 0 is another combination, which is considered as another label 2. 0, 1, 0, 0 is another unique combination, right? So it is considered as 3. Now 0, 1, 1, 0 has already been labeled as 1. So this again gets labeled as 1. 1, 1, 1, 1 is another new combination, which gets labeled as 4. And 0, 1, 0, 0 is already been captured. So this way we convert our labels, we transform our labels into newer labels. And now this becomes a multi-class classification problem. Now you have 4 classes here and you have 6 data points, and you can apply a simple multi-class classifier and generate the outcome. So let's say you have a data point X4 and you get an outcome for it 1, which means that 1 belongs to this particular power set. So X4 belongs to Y2, Y3. I hope this makes a little sense. And then adapted algorithms, as I explained, so few algorithms are adapted to directly perform multi-label classification. We need not have to do such kind of transitions or label transformations, or even handling, using multiple classifiers, because let's say we want to predict a lot of labels at once. So generating a lot of classifiers can be memory consuming. So that way we generally use the adapted algorithms. And then we use the ensemble approaches. So these are various techniques in broad which can be used to perform a multi-label classification technique. Now, how do we evaluate such examples? We saw earlier that multi-class classifications are evaluated using precision, F1, using accuracy if it's a balanced data set, and if it's not balanced, then precision, recall, F1, and AUC numbers. But what happens when you have multiple labels associated, when you have the outcome in the form of 1, 0, 1, 0. So you have multiple labels there. So how do we evaluate it? So there are like two methods basically to evaluate such problems. One is a label-based measure. So label-based measure would involve that we go on calculating either it in the micro averaging format or a macro averaging format. So what happens in micro averaging format is we sum. So once we get our, let's say we have 4 labels and we have 100 data points, and then we have the entire vector out of which all of these 100 data points get classified into these 4 labels, right? So one can be 0, 1, 0, 1, one can be 0, 0, 0, 1. We have multiple such combinations. Now what we do is we identify how many true positives are there and then how in total. So one true positive would mean if 0101 is present, then another output should also be 0101. So that now for each of these label, right? Let's say we have 0101 and we also, okay, let me explain this in a better format here. Okay. Is the text. So let's say we have an outcome which is 0101. And let's say we have predicted for it something which is 0001, right? Now, in these cases, only the final label is actually a true positive. Now, this particular label, which was actually supposed to be 1, but got identified as 0, this is a false negative. And okay, let's say something like we have 1 and which got identified as a 0. So 1, 0, 0 then becomes a true negative, and 1, 0, no, sorry, 0, 1, yeah. 0, 1 becomes a false positive. So, we have 4 labels out of which we can identify all of these matrix, right? We have the true positives, we have the true negatives, we have the false positives, and we have the false negatives. So out of these labels, now since we have multiple labels out of here, we calculate how many such true positives are identified, how many true negatives, how many false positives, and how many false negatives. So we do a count of these. And once we count these numbers, we can do a summation of these to calculate the micro averaging precision. So the total count of true positives divided by total count of true positives plus total count of false positives. Similarly, micro-averaging recall is identified, and then for calculating an F1, we take a harmonic mean. So F1 is basically taken as a harmonic mean of these precision and recall. Now, in case of macro-averaging techniques, rather than doing it on a very deeper level for each of true positive, true negative values, for each of these classes, we identify the precision recall values. So let's say we have 4 classes, we'll have 4 precision recall values, and then we sum it up. So we do the precision recall of the data set for class 1, precision of the data set for class 2, similarly up till, let's say 4 classes are there and up till 4, and then we divide it by 4. So we do an average precision, and similarly we do an average recall. So these are the label-based measures that are used to identify how well our multi-label classification has performed. There are example-based measures also, like for example, Hamming loss. So Hamming loss is nothing but just the proportion of how many labels are incorrectly predicted. So let's say if a 1 is predicted as a 0, that becomes one such incorrect prediction. Or if a 0 is predicted as 1, it becomes another such incorrect prediction, right? So then we sum how many such incorrect predictions are there based on the total number of predictions that are given, right? In order for identifying that, we generate what is the Hamming loss number that is there. So these are example-based measures to actually evaluate such classifiers. So understanding these evaluations in detail, So what happens is, let's say there are multiple cases. Okay, let's say our model doesn't predict the expected labels, but it also doesn't predict extra labels. What this means is here, okay, let me explain what there can be multiple cases, So in first case, let's say we had something like 1010, right? And our model did not predict the expected label, which means it got something like 0010, So this one, which was supposed to be expected, did not get predicted. But there's also no false positive over here, that the model did not predict anything extra, So in such cases, we have high precision numbers because whatever is getting predicted, that's getting predicted correctly. Like we can see that this number is getting predicted, which is getting predicted correctly. Other three are not getting predicted, and we are missing out on some predictions, which is okay, which gives out a low recall. So such cases are termed as high precision, low recall. Okay. They can be an opposite scenario, opposites. So what does the opposite scenario mean? So opposite scenario would mean something like we have 1 0 1 0 and we have 1 1 1 0. So this means that whatever we are supposed to predict, we are giving out extra predictions. Like this is an extra prediction that kind of came out. So whatever we are supposed to predict, that we are predicting correctly. So it's a high recall, but low precision because there are extra predictions out here which we are not getting. So there are more false positive numbers there. So our ideal cases would mean high precision, high recall. Whenever you evaluate a model, you want high precision, high recall, high F1, high accuracy numbers over there. But in certain cases, if the data set is imbalanced or there are certain other nuances like a noisy data or an overfitted data, these might not happen. So what we tend to do is we use a threshold in order to ensure that we get what we desire for. We consider the trade-off between these precision and recall values. So so what we can do is if we increase the threshold, we can have a high precision value. And if we reduce the threshold, we can have a high recall value. So let me explain you the applications where high precision and high recall value actually make more sense. In general, whatever data set we might have worked upon over Kaggle or over some other competitions, they tend to give out, we don't care a lot about, what out of these two, what we want to focus more on. But in real world applications, when we're actually working on real world data set, we might not get actual high numbers on both of these metrics. So we can prioritize based on business requirements. So for example, if we are using it in a medical diagnostic case, so for example, skin cancer detection system, we can never afford to label a cancerous case as a non-cancerous one, because if a model identifies that it was a cancerous case and you missed out on it, then patient's life is at danger, right? So the opposite can still be true. Like even if you label a non-cancerous patient as a cancerous patient, you can again go for a second round of testing by the doctor or evaluation and then again rule it out. But you cannot miss out on any of these cancerous patients. So what you do, you want to minimize the false negatives and you want to maximize the recall. So you want to predict as much correct as possible. Even if you go for extra predictions, it's fine. But what you're predicting, you're capturing, your capture length should be as high as possible. Now, in case of recommendation system problem, you are more concerned with recommending correct. You want to recommend correct. You don't want to recommend whatever is possible. You want to be very specific with your recommendation. Even if you miss out on something that the customer likes, is still okay. But whatever you're recommending, that has to be correct. Then here our goal is to reduce the false positives. We want to focus on precision, that whatever you want to predict, that has to be very accurately correct, because then the user would feel that a lot of rubbish recommendation is here and then your recommender will not work correctly. So I hope this is making some sense into where we can prioritize precision and where we can prioritize recall. So I'm done with the theory aspect. If there are any questions, I can either take it now or I can take it in the end. I want to do a few little hands-on on the coding aspect of multi-class and multi-label classification. Let me just show one thing. Okay. Okay, I'll explain. So the data set that I have taken is a very basic data set. So for multi-class classification, I have taken two such data sets. One will be an iris flower data set, which most of you would have taken a look into. This is just to explain in a very basic format what different algorithms we can use on a very basic data set, And then we go deeper into a text data set, which is a news group data set. And then we understand more in detail on how in a slightly complex manner we can perform this. So I'll go very slow. If there's certain explanation is required or if somebody wants me to pause, do let me know. Okay. So this iris flower dataset, it consists of 50 samples from each of these 3 species of iris, setosa, virginica, and versicolor. And then 4 features are available: the length and width of sepals and petals in centimeters. So let me just run this. So I can also show you the dataset here. Let me just show you the dataset. So a very basic form of this data set is the sepal length, sepal width, petal length, and petal width are available in the form of centimeters. And then it's labeled as one of the species. So this is the 3-class problem. And we have equal outcomes for these. So now we want to do certain EDA on the data set. We want to understand what the data set is, how the features are present with respect to the label. Are there any outliers? How are the features correlated? What is the capture for each class? And then we go deeper into performing the classification. So we do we use Seaborn for all these plotting. So we plot the density with respect to petal width. So for example, let me explain one in detail and then we can go for each of these features. So what this would entail is, for a petal width kind of scenario, if the petal width ranges lower than, let's say, 1, it basically or more or less captures the iris setosa species. So this is a very clear definition that if the petal width is less than 1, then it involves a iris setosa species. While on the other hand, if the petal width is between 1 to, let's say, 1.1 or 1.2 or something like that, it is very clearly differentiable as iris versicolor. But if the petal length goes slightly higher than that, so in the ranges between 1.5 to 2, there is an overlap. So it can belong to both of these classes. But if we go slightly higher, so more than 2, if a petal length is more than 2, then it's clearly belonging to iris virginica. So this means using one feature, we can deep dive and understand that if this feature ranges from this range to this range, what class does it belong to? So similar analysis has been done on other features as well. Like for example, for sepal width, it is not very clearly identifiable that, if the sepal width is in certain ranges, then which class does it belong to? Similarly for sepal length and then for petal length. So petal length also becomes very clearly distinguishable. So petal length ranging less than 2 belongs to iris setosa. Petal length between 3 to say 4.5 belongs to iris versicolor. So for 4.5 to 5, it's still complicated. I mean, it can be either of these two. And then from 5 onwards, it's clearly iris virginica. We also identify box plot, and then we figure out whether, how much outliers are present for each of these classes, for each of these features. So for example, once we understand this box plot in detail, we can figure out the numbers, we can figure out the median values, we can figure out where the outliers lie, and we can remove outliers if they are less in number. So there can be multiple EDA techniques that can be applied on the data set. So now So now I'll label these data set and understand the correlation metric. So we'll understand the correlation between different features versus the label and what this number entails. So for example, having a correlation of 0.81 between petal width and sepal length would mean that these features are highly correlated with each other. Similarly, petal length and petal width having 0.96 means these features are highly correlated. So in some cases, when the features are very highly correlated, we can either go by removing one such feature, and even after removing one such feature, our predictions would still be more or less correct. Then again, we go for pair plotting, identifying that in the 2-dimensional space for each of these feature vectors, how can we clearly distinguish between the two classes? I'll share all of these resources in detail. I'm just explaining how, we can go identify certain EDA techniques, how we can figure out understand the data in detail, and then do a classification. So let's say we split the data. For now, we have taken a split of 0.20, which means 20% of the data goes into testing and the rest of the data goes into training. So one by one, we'll look at the algorithms. We'll plot do a logistic regression fit on the data. Logistic regression is a very basic classification technique. Once we do, because this is a very small data, we have received an accuracy of 1 on the test set, because It's like 50, 50, 50, and there's just 4 features. So it's very clear that our model has been clearly overfitted on the test set, but still more or less clear enough to explain how logistic regression and how other classifier techniques work. Similarly, we can have a support vector classifier. We can fit a support vector classifier, and then we can generate the accuracy number. We can also have a random forest classifier. A random forest classifier is a slightly more on a complex ensemble technique. And then once we do a random forest classifier on top of it. So this is just to explain, there can be multiple such classifications, which techniques which can be used. So we can also identify the classification report. So this classification report is something that can be in detail understood. So this for each of these, so since we have these 3 classes, we identify the precision, recall, and F1 value for each of these classes and the support. So support would mean how many of these data samples belongs in the test set belongs to this class. So 9 such data points belong to 0, 11 data points belong to 1, and 10 data points belong to 2. And then each of these values, the precision, recall, and F1 numbers are available. Now, so these are very simple machine learning techniques. We can also use a artificial neural network. So we can use a sequential Keras model with adding a dense layer, adding a softmax layer, applying this categorical cross entropy using accuracy as the metric, because both of these, all these 3 classes are equally balanced. And then we can run multiple epochs on top of it and get the test accuracy. So this was very basic definition of how we can run a multi-class classification problem using multiple such algorithms. Now we type a little bit complex into the 20 newsgroup dataset. So what this dataset is, this consists of 18,000 newsgroup posts. So 18,000 text samples in a very basic format on 20 topics. So our entire data will be divided into, let me just run this. So our entire data will be divided into these 20 topics, and these 20 topics, so we have 18,000 data points divided into 20 such classes, right? Now this is classified into our training set and our test set. So, okay, how we will be approaching a text multi-class classification problem is, because since it's a text number, we'll be converting our text into numbers. So for now, we have used a TF-IDF vectorizer, but since we are in 2023, there have been multiple such advances on how we can, I'll just explain, I've not put it in the notebook here, but I'll explain in text format. So for example, if you have a text available with you, right, which is, okay, let's say if you have a text available with you, right, let's say, not going into the news group detail, but in general, let's say I want to purchase a new car today, right? This is the text available with you, right? Now, since the advance of NLP, there have been multiple techniques which can be used in order to convert this text into numeric format. So very basic technique is to apply one hot encoding based on the bag of words technique. Then you can, other than bag of words, you can go deeper into this. You can identify a TF-IDF technique, which we have used here for now. TF-IDF will still give you the term frequency into inverse document frequency, and it will still capture some based on the frequency only. But let's say you don't want to go based on frequency, you want to also capture the context. Then we have some earlier embedding techniques. We have word-to-vec techniques, we have glove embeddings, which are very famous embeddings available online. We can use these embeddings for each of these words and sum it up and get a sentence level embedding. Coming into another layer, adding another layer of depth on top of it, instead of using these embeddings, we can go with another layer of depth. We can use BERT embeddings. So these BERT embeddings are nothing but giving more context to our actual text dimensions, So whatever word-to-vec and glove kind of lacked, capturing the different meanings for the same word, or capturing different context, or capturing a longer context, all of these BERT embeddings have kind of captured. So we can use any of these embeddings to convert our text data into a numeric format and then run multiple classifiers on top of it. We can run an basic neural network, which I've used here. We can run an RNN technique, We can run an LSTM technique. We can run a GRU model. We can also try with the CNN model. CNNs have also performed to be well enough good on text. We can try with a combination of these. And in further depth, we can also use a BERT model. So BERT for classification, which will be a higher level of complex model, which will have multiple transformers. And then on top of these transformers, we can get the output. So our goal is to actually output one out of these few classes, but there are multiple techniques that can be used to do so. Okay. For this particular example, we've just taken a very small subset of the train set. This is like 18,000 numbers. We've just taken 2,000 such train sets and 4 such categories out of 20 in order to run it in a faster format, right? So once we run it, we get that we have 4 such target categories: atheism, religion, graphics, and space. And we have 2,000 such news articles belonging to 4 of these categories, right? We do a TF-IDF vectorizer. We convert our data points into TF-IDF vectorizer, fit it on the train set, and then we run a multinomial naive-based classifier on top of this. So what this involves is we capture the test set for these 4 categories. We transform our test set. We fit our classifier on the training set. We generate the predictions on the test set, and we get the F1 score. So as you can see on the macro, F1 score on the test set is 0.88 for a multi-class classification problem, right? And the test set is 1353 of such samples. Okay. Now we can also go ahead and run instead of a multinomial naive-based classifier, we can run a Keras model. So over here, we have captured a sequential Keras model, which has a dense layer. Then it has a ReLU activation on top of it, a dropout layer in order to ensure that it doesn't overfit. Then another dense layer, ReLU activation, dropout. Then another dense layer with 4 as output because we have 4 classes, and then on top of it, a softmax activation. We use this particular combination of model for now. We can also go into hyperparameter tuning, tune such models, identify multiple combinations of layers and multiple combinations of parameters there. We convert our data and then we fit the model. Once we fit the model, we run multiple epochs, and on batch size, once we fit the model, we identify that on the test set, we receive an accuracy of 0.76, right? And then once we generate these numbers, we generate the precision, recall, F support, and support numbers. We see that the precision is generally high for the first 3 classes, while slightly lower for the 4th class. The recall is lower for the first class, higher for these classes, and F score is considerably harmonic mean. So understanding this classification report over here, out of these 4 classes that we have, we can capture each of these metric, and then we can specifically understand that why for each of these classes our model is performing well or not performing well, and then go deeper into this. For now, we can still go with accuracy because our data is more or less balanced. But in cases, let's say, for example, 0 class was having 1,000 data points and other classes having these many data points, then instead of looking for accuracy, we could have looked for more macro average or weighted average numbers, So this was about multi-class classification in general. Let me go and open a multi-label classification problem. So now we have understood how multi-label class classification can be done. Let me explain how we can do a multi-label classification. So for a multi-label classification, again, we have taken a text data, which have multiple Wikipedia comments, which have been labeled by human raters for toxic behavior. So toxicity can involve these few classes, and it can be a combination of these classes as well. It doesn't need to necessarily go into one of this class. It can be a combination of these classes. So again, we run this model. Okay. So for example, here we have the, I'll explain for one such data point, right? So for one such data point, why the edits are made under my username, such kind of comment text. This is not belonging to either of these data points, right? So in this format, you have a output label vector of 0, 0, 0, 0, 0, 0, right? How we understood initially that we can have an output label vector which can have multiple ones in it. In that way, we can do a multi-label classification. We check for missing values and identify that for this particular data, there is no missing values. Then we go further into detail, and then we figure out, that what is the category distribution for each of these categories. So out of our entire corpus, majority of these belong to a toxic category. Then severe toxic is 1595, obscene category is 8449, and then others. So this is the category distribution of how many data points are there. And as you can see, this is a kind of an imbalanced data, because in certain labels are very lowly present, while there are certain labels which are present in most of these data points. Now on further identification with how many such comments are there with multiple labels. So we see that there are 6360 comments which have one label, 4209 with two labels, and then further on. So there are very few data points which have all of these labels, while there are very like majority of data points with such one or two labels over here. We go into further detail, and then we start with the EDA on top of this data, and then running a multi-label classifier. So basic EDA would involve cleaning out HTML context, cleaning out punctuations, cleaning out alphabets. So just making sure that data is more or less alphabets. And then once we apply all of these, our data becomes very clear. So for example, initially, if you would have seen the first data point, let me just show. We had a backslash and we had capitals over here. We had, let's say, apostrophes. We had commas. We had multiple special characters, not just alphabets. So we cleaned all of that and made our data converted into lowercase alphabets, Then we removed the stop words. Stop words are nothing but just the very commonly used words, and we remove the stop words out of these. We go for stemming the data. Stemming would mean we convert a lot of verb numbers into their basic inherent capture. So for example, something like discussing would go into a discuss, or planning would go into plan, We split our data set into train and test set after doing all of this EDA, converting our text into numeric format. So putting a TF-IDF vectorizer like how we did initially. Again, we can apply multiple such embedding techniques over here. And then we go with multiple kinds of multi-label classification. So one way is to just do a one versus rest classifier. So we use a logistic regression. For each of these category, we fit our classification, our entire data. So this would mean that, let's say we had the first category. So our entire data will have first category label as 1 or 0 and rest as 0, We fit the data point, and then for each of these category, we separately identify what is our accuracy. So for toxic comment, our accuracy is 0.91. Again, we have very high accuracy for threat comment. So for each of these classes, we separately identify them, and then we capture the final label out of it. We can also use Scikit multi-learn to get a binary relevance, like how we explained. So we apply binary relevance on top of Gaussian naive-based classifier, and then we generate an overall accuracy number, We can have a classifier chain method. So classifier chain method would mean that we'll have multiple classifiers, one on top of the other, and then we get an accuracy. So we see that using a classifier chain, we get a slightly higher accuracy as compared to binary relevance. But the usage time has also increased, because what happens is we keep we use initial features also into consideration. So it's A with the feature vector. So that means the X data point along with Y1 feature vector is again used for capturing Y2. Then X, Y1, Y2 is again used for capturing Y3. So we see that CPU usage has increased, Now the label power set, where we first convert our data point into applying the label power set, which means that we transform our problem, like how we saw that we can have multiple such vectors, and we convert those vectors into multiple classes, and then we run. So we get an accuracy of 0.90. So I think I have also added some resources on, where these kind of data sets or where these kind of techniques can be applied into the slide. And okay. I'll just stop sharing. I'm open to questions if there are any such questions.
Yes, guys, before we proceed to answer your question, I'd like to request the attendees to please fill in the poll about feedback, as it helps us to conduct more such sessions. You can go forward with the questions.
Yeah. So, okay. I'm looking at the Q&A. Okay. Can I explain again the part where I explain softmax over multi-class and softmax over multi-label? Okay. Let me just, okay, I'll explain that in a minute. So which approach is best in case of a multi-label classification? So I think it more or less depends on your data, but if you say the best approach, then ideally the best way, if you have a huge amount of data available with you, then the best way is to go and apply neural networks on top of it. And neural networks give you the flexibility of actually predicting for each of the nodes, you can have a binary classifier and you can get the output from that. And that kind of works well. Why we're using many classifier methods? So many classifier methods is suggested in case where there are a lot of classes available and your one inherent classifier is not able to capture for each of these classes. So for example, you have 200 or 300 such classes available and you don't have sufficient data points for each of these classes. So if you just train one such classifier, it is very likely possible that your classifier is going to be predicting very nice results for the ones which have nice data points, but the ones which are in minority will not be predicted properly. So one way is you can either balance your data set if you have the flexibility to go for it without corrupting the data. But if you don't have such flexibility, then it's best to go for the many classifier method where each of these classifiers is actually trained on that particular class so it can give out the best possible result. Keras, ANN, what is input shape? Input shape will depend on the number of dimensions. So for a TF-IDF vectorizer with a certain vocabulary, like for example, if you use a glove embedding, the input shape will be a 300 dimension problem, right? If it's a 300 dimension. But if in case of, let's say, BERT embedding, the input shape can go up to 512 dimension or something like that. So that depends on whatever input we are using. Can you show the slide where you have the GitHub links again? I'll ping them in the chat available. How to deal with imbalanced data in image data set. Okay. Image augmentation is definitely one way to go about it. We can, there are multiple kinds of image augmentation techniques available. It's, you can vary the pixel ratio. You can vary the direction of such images. You can flip such images. You can add some noise to those images. You can change the background color. There are multiple kinds of image augmentations that can be applied to image data sets. Okay. Using neural networks to do sentiment analysis or classifying text by sentiments. So right now we're just, I'm not very clear about this question. Is it about the multi-class or the multi-label classification? So if you can just ping again. Shall we choose a model based on the nature of data, or we should apply all the models and then check the accuracy of all of them? See, the first step is to do some research and figure out and understand the data in detail. Once you understand the data in detail, um, it will become slightly clear to you as to which models will work and which won't work. So, for example, if you have, let's say, a very huge dimension data, right? You have multiple data points with a lot of noise or something like that in it. It's generally advisable to go with deep learning techniques. But if you have a smaller data, which is more clear or something, it's not advisable to go with deep learning techniques. You can go with random forest, XGBoost, and more or less in the machine learning scenario, XGBoost and random forest have tend to given best results irrespective of the kind of data you apply. So they have surpassed the results of logistic regression, support vector machines, naive Bayes, KNNs, and all other classifiers. So usually people go ahead with random forest and XGBoost classifiers, but still you can keep on and try 4 or 5 of these techniques based on after you understand what the data is all about. So I'm just going to explain the first question again, where applying softmax over multi-class and softmax or multi-label. Let me just share my screen again. Okay. So what I was trying to actually explain was that, let's say we have these three classes in the form of an output. If our goal is to do a multi-class classification, we are going to have a softmax activation on top of it. And the output that we will be getting is something like a vector of probabilities for each of these class, which sum up to 1, because softmax gives us sum up to 1. So it can be 0.7, then 0.2, and then 0.1, something like this, right? And then we choose the max value out of these. We do argmax, and we, let's say we get 0.7, which means that this data point belongs to the first class only, right? This happens in case of a multi-class classification. For a multi-label classification problem, we don't do a softmax. Rather than we apply sigmoid on each of these nodes. So what we do is, for, let's say for this particular node, for the first node that we have over here, we apply a sigmoid and then we generate a probability value. So sigmoid will give you one such probability value, rather than doing, for each of the node, you will get one such probability value. And it doesn't necessarily need to, the sum of these three doesn't need to sum up to 1. They can sum up to any such number. So let's say you, for this particular class, you get a probability value and you get a sum up of 0. Let's say 6, For the second class, you get a probability value of 0.5. For the third class, you get a probability value of 0.2. Now you can apply a threshold of, let's say, 0.5 or 0.6 or something like that, and then figure out whether the output label is supposed to be 100 or it's supposed to be 110 based on that threshold. Once you get that output label, you compare that output label with your actual output label and then do the backpropagation. I hope this clears out the doubt.
So I guess our session is over. So thanks a lot, Aanchal. On behalf of Analytics Vidya, I'd like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more session with you in the future. The LinkedIn profile of the speaker shall be found in the chat section. You can look into that. I hope you guys have filled in the feedback poll, and if not, I request you to please fill in the poll about feedback, as it helps us to conduct more sessions. If you wish to conduct a webinar or are facing difficulty in registering, connect with us at editor@analyticsvidya.com. So we'll be back with another session of the DataHour series. The link is provided in the chat section. Till then, bye-bye and keep in. Thank you, ma'am.
Thank you, everyone.